Okay, sounds a little different than usual. So welcome, Susanna, welcome, Alexi and Rigny and Stephanie and Bruno and Adam and Diego. Thanks for coming. Let me jump to the quiz. I'm going to share my quiz screen. Okay, so we have our quiz. And that one. And the question is, consider the function f of x equals e to the negative 2x. Find the Maclaurin series for this function. So kind of the purpose of this is if you want to find a Maclaurin series, we draw a table and look for patterns. So let's do that. So I'm going to insert table. Just do a bunch of rows. We're going to have like so. And we're going to have n. We're going to have fn. Of x. I guess I should put parentheses there. So it's not a power, it's a derivative, the nth derivative evaluated at x. And then the nth derivative. And if it's a Maclaurin series, where are we evaluating it?
0.
Yeah, it says 0. So Maclaurin series are typically the easier series because you can just plug in 0, and 0 is usually easier to plug in than anything else. Okay, so let's start out with n equals 0. N equals 0. Remember, the 0th derivative is just a function. So that's just e to the negative 2x. And if you plug in 0, what do you get?
One.
Yeah, we just get 1. And then we go for n equals 1. We go until we find a pattern. What's the derivative of e to the negative 2x?
Negative 2e to the negative 2x.
Yeah, negative 2e to the negative 2x. And if I plug in 0, I get?
Negative 2.
Negative 2. If I plug in, okay, so if n is 2, take another derivative. And what I recommend is don't multiply out. So we're going to have a another negative, so it'll be positive now. It'll be 2 times 2 e to the negative 2x. Any questions on that? And yeah, I mean, it's not wrong to multiply, but it's easier to see the pattern if you don't multiply. That's all. So it's not like mathematically incorrect or something, but I recommend not multiplying so you can see, is it a power? Is it a factorial? Is it all odd numbers? You know, what is it all even numbers? What's up? And we'll see that on the next one. Probably it'll be obvious. So if I plug in 0, I get 2 times 2. So let's go for n equals 3. And if we have n equals 3, again, another chain rule, you get 2 times 2 times 2. And if this one's negative, e to the negative 2x. And that's negative 2 times 2 times 2. And at this point, you might see the pattern. I'm hoping you do. So let's see what n is going to be. So we have, notice it's 1, negative 1. It's positive, negative, etc. And that's always going to flip back and forth. And if it flips back and forth from positives to negatives, then what do you always have?
Negative 1 to the power of n, or n plus 1.
Yeah, exactly. Negative 1. And what I like to do is I'll just write power n and then check it. And if it doesn't work, I go plus 1. So then plug in 0. And negative 1 to the 0 is positive 1, and it works. That means I don't have to do a plus 1. So that's the first part. And now what's happening with the 2's? Notice if n is 3, we have 2 times 2 times 2. Okay, so if we have n instead of 2, then what are we going to have?
two X to the N.
No X, so I don't see any X's in these, right? You get their idea, but no X. Does that make sense?
Yeah, I was just considering the other X that's usually there to the N and combining them.
Yeah, that's
but-
gonna happen later, but right now we're just finding the nth derivative evaluated at 0. That's all we're finding. And then we're gonna put it all together with a power series. Okay, Maclaurin series. But right now we've found the nth derivative, and that's really the hard part. The next part is just plugging into the formula. So now I could just say f of x is equal to, and now I'm gonna have a sum. And then if you want n equals 0 to infinity. And then what we get is -1 to the n, -1 to the n, times 2 to the n, and then times x. And it's Maclaurin series, so it's not x minus anything, it's just x to the n. Any questions? Any questions on question number 1? Oh, I forgot to divide by n factorial. Should have had a question. So then divided by n factorial. Because that's part of the series. Any questions at all on the answer to question 1 and the whole process? Okay, so as you can see, it's finding the nth derivative is the hard part. The rest is just plugging in. Okay, if there's no questions, let's go to question 2. Now it's find the second degree Taylor polynomial of degree. So now I guess I shouldn't have said degree 2 twice, but degree 2 centered at 1 of f of x equals ln of x times the sine of x. Yeah, let's see, if you combined -1 and 2 to the n, yeah, that's technically correct to combine those two, but it turns out typically you don't want to, because this -1 to the n shouts out it's an alternating series. So that's why I usually like to pull it out, because then you can kind of see what's going on. We got an alternating series, we get some kind of binomial looking thing, and this part is just Taylor series stuff or Maclaurin series. So typically you pull out a -1 to the n or -1 to the n plus 1. Yeah. Is it wrong to not pull it out? No, but it's just a little easier to work with. Like, for example, if you're asked to find out if it converges or not, or what its radius convergence is, or interval of convergence, then it helps to have it pulled out because you can be taking an absolute value. And it just goes away. Okay, so let's go and find the second degree Taylor polynomial centered at 1 of f of x, ln of x, sine of x. By the way, I should mention, because this is important, if I asked you to just find the Taylor polynomial, forget of degree 2, Taylor series, this is horrible. Okay, this is really bad. Any guess on why it's really bad?
You're using the
would take
quotient
too
rule and
long.
the product and everything.
Yeah,
So
you're going to have a quotient rule at every single product rule, and then quotient rule at every single derivative of an infinite number of them. So that wouldn't have, in my opinion, it wouldn't have been a fair question. But since it's degree 2, we can do it. Okay, and to find it at degree 2, it just means we need to find out what is f of 1. That's the first thing, very simple. And that's easy. I hope you can all just look at it and tell me immediately. What's f of 1?
0.
Yeah, f of 1 is 0, because ln of 1 is 0. You don't have to know sine of 1, just 0. Okay, now f prime. Let's go f prime of x, and then I'll plug in 1, because that'll help, because we're going to need f double prime also. So f prime of x. And what rule do we have to use to find the derivative of f? Not a trick question. You're supposed to all know. Yeah, product rule. So we take the derivative of ln of x, which is 1 over x, times the sine of x, and then plus the derivative or ln of x times the derivative of the sine of x, which is cosine of x. Any questions at all on f prime of x? So f prime of 1 is what? And you're not going to give me a pretty number, but it shouldn't be too bad to write down.
I left sine of 1.
Yeah, sine of 1. Yeah, sine of 1. Sine of 1 is not anything nice, by the way. But we can write sine of 1. It's not hard to type. Okay, and then we want the second degree, so we need f double prime. So f double prime of x is equal to, and now for the first one, let's use a quotient rule. So that's going to be low, which is x, times the derivative of the sine of x, which is cosine of x, minus high, which is sine of x, times the derivative of x, which is 1, so sine of x, all over x squared. And then plus, and then we got to use the product rule for ln of x cosine of x, and that's going to be 1 over x times the cosine of x. And then that's plus. And then we're going to have ln of x sine of x, and it's going to be a minus because it's negative, because derivative of cosine is negative sign. So we're going to have ln of x sine of x. So f double prime of 1, we got to plug in 1, is what? It's not too bad, actually.
I have 2 cosine of 1 minus sine of 1. I
Okay,
don't know if that's right, though.
so let's take a look. So we now have a 1. So we have x. So we have 1 cosine 1 minus sine of 1 over 1, which is just cosine of 1 minus sine of 1. And then we have plus 1 times cosine of 1, and then minus 0. So that was right, 2 cosine of 1 minus sine of 1. And now we're ready to answer the question. The question is, find the second degree Taylor polynomial degree 2 centered at 1. So what we do is we take the first term, which is just 0, plus we have sine of 1. And then it's over 1 factorial. You don't need to write that down because 1 factorial is 1 times x minus 1 to the 1, and then plus, and then we're going to have 2 cosine of 1 minus sine of 1, and then divided by 2 factorial. 2 factorial is 2. And then times x minus 1, I think I'll write times x minus 1 squared. Any questions? Any questions at all on question 2? Any questions? Something I didn't do, and I think it's worth doing. I didn't ask you to do this on the quiz, but I think it's still worth it, is to plot it. Just take a look at it. Oops, I don't want that one. I want that's one Decimus. There we go. And we had ln of x times the sine, was it sine of x? And that's what it looks like. And here's x equals 1 right here. And now let's see what we got. And I want to just show you that it does what it's supposed to do, because I didn't actually show you that with last time. So I figured I better show you what's going on here. And let's see if I can copy and paste into Desmos. Okay, so if you look at this, this is the second degree Taylor polynomial for this function. And if you look at it, it does pretty well. In fact, especially if you zoom in a bunch. It does pretty well for a while, and then it doesn't. If you do a third degree Taylor polynomial, it'd do even better. Fourth degree, it does better. So the higher the degree Taylor polynomial, the better you are to the curve. Does that make sense? Kind of an easier one, because we did this one also, is if instead of ln of x, we just have sine of x. There's y equals sine of x. And I don't know if you remember the sine of x, the first is this x. And just watch how it gets better. And the next is going to be minus x cubed over 3 factorial, which is divided by 6. And you'll notice it's starting to get better. And then the next one is going to be x to the 5th divided by 5 factorial. Okay, it allows. And look to see what's going on. Is it getting like a better and better approximation? Right? Do you see that's a lot better than a tangent line, isn't it? The tangent line isn't going to do this stuff over here or over here. And then if I go to the next one, minus x to the 7th over 7 factorial, then it's even better for sine of x. Any questions on kind of the point of using a Taylor polynomial to approximate a curve? This is the best 7th degree polynomial approximation to the sine of x. And you can see that it does a pretty damn good job as long as you're between -3 and 3. Okay. Probably around negative pi and pi actually is probably where it starts losing it. But anywhere else, it's like right on. Okay, and then if I did 9, if I did the next bunch of them, it'll go even farther out. And it'll get better and better as an approximation, which means you can go farther and farther out and have less and less of an error. Okay, in fact, if you zoom in a bit, how about one more? It makes it look like the sine of x is just a polynomial, isn't it? Right? Because if I didn't even graph the sine of x, now you can't see it, you would have guessed that this function right here, the graph, if all I showed you was a graph, you probably would all told me that looks like the sine of x. That's just the sine of x, if you didn't see the equation. Do you agree? But as soon as you zoom out a bit, now all of a sudden it doesn't look like the sine of x anymore. Any questions on kind of the whole purpose? Because it's important to understand the purpose of what we're doing. The purpose of what we're doing is to be able to take a function that isn't a polynomial and find a polynomial that is very, very close to that function for as far as you need to go. Okay, so if you needed to go, up to 6 or so and -6 to 6, this polynomial is not long enough. Okay, on the other hand, if you just needed to go from -3 to 3, this polynomial is perfect. Okay, it does everything you need for sine of x. Any questions on that idea? Okay, because I want to make sure that you don't have more questions on this. Any more questions on the quiz? Any questions on the quiz? Okay, it says no more questions of quiz. I wanna go to the calendar. I think that's important. And look to see what's up. Because this is about time to start, getting ready. So the first thing is we are here on the 11th. You just had your quiz on Taylor Maclaurin series. Today we're going to be talking about working with Taylor series. And notice that's it. It's the last thing we talk about. Because the assignment due, this is the list of things to do. And the assignment due on Monday is 6.4. And there are no more assignments after that. So today is our last day of calculus. And for some of you, possibly, this might be your last day of math in your life. Isn't that weird? You've been doing it since you were, 5 years old. And this could be your last math class. But for a lot of you, hopefully a bunch of you, I always like to encourage people to do more math. You still have, at least another year. Maybe if you're like me, you'd have like 7 more years of taking math classes. But definitely, or that'd be 8 more years, sorry. But the point is that we're at the end of this class. So today's our last day of new material. So which means on Monday, you'll have a quiz on 6.4. And then I'm just going to review for exam 2. Okay, answer questions and review for exam 2. Then on Wednesday's exam 2. And the rules and stuff is exactly the same as exam 1. Just to let you know. So I let you have 2 hours if you need it, just to let you know about that too. And then on Friday, I'll go over exam 2 and then we'll review for the final exam. Okay, and then in 9 days is your final exam, and note that it starts at 8 a.m. and don't get mad at me. I just use the start time that the college uses. So it's earlier than you used to. Sorry about that. But again, don't shoot the messenger on this one, as I do what they tell me I have to do. So your exam goes from 8 to 9:50. I'll probably give you till 10, because that's what I do in regular classes. If you need an extra few minutes, I do it, and then it'll close. So a week from Monday is really the end. Okay, after that, I'll be grading, but you're done. Any questions on the calendar? Any questions? Okay, I'll probably remind you again on Monday. And by the way, on Wednesday, there is no Zoom section because you just take a test. So we only have 2 Zoom sessions left, and they're both review days. Okay, and just a note, a couple notes. One is the exam 2 only covers post-exam 1, which means basically sequences and series and Taylor series and polynomials. So that's what it's going to cover. But the final exam covers everything. So if you're going to be starting to study for the exam this weekend, I recommend, working on chapter 5 and 6. Any questions? Any questions about anything as I go back to my stuff to do? Okay, if there's no questions, I'm going to start doing the binomial series. I'm going to do it kind of just as a little reminder. Let me insert an equation. So let's suppose we have x plus 1 cubed. Who remembers how to do that? Actually, let me write it. I know it's the same thing, but I think it'll be easier to see. 1 plus x. It's the same thing, cubed. Who remembers how to do that? This is not anything fancy. You did this in probably intermediate algebra. Yeah, third level FOIL you could do. Okay. And when you do it, I'm not going to do the whole thing. I'm just going to write down the answer because I got it. Because there's another way to do it, which I want to talk about. So it's 1 plus 3x plus 3 x squared plus x cubed. Does that ring a bell at all? What if, now I'm going to get evil. Instead of 1 plus x cubed, what if you wanted 1 plus x to the, how about 20th? Could you do this? Do you remember this? Okay, you probably learned this once, but you probably also forgot it. That's my guess, but I might be wrong. Maybe you all remember it. So if you do, tell me. No, without a computer. Don't need a computer. Definitely don't need to integrate anything. There's no integral here. Okay, so this happened, and it was actually used in first quarter calculus when I proved the power rule. That we did x plus h to the nth power. And what that is, if you remember, it's going to be 1 plus 20x plus, and then it was 20 choose 2. Okay, so it was 20 choose 2, which, by the way, is 20 times 19 divided by 2. X to the x squared. Does that ring a bell at all? And then plus, and then it's going to be 20 choose 3. And 23 choose 3 is 20 times 19 times 18 divided by 3 factorial. X cubed. And then I'm just going to go plus dot dot dot. Do you remember this happening at one point in your algebra classes? Or the proof that I did in September? Might have been October, late September, early October. You remember that? So this happened. Okay, well, you don't remember, I know. Not everyone has like a perfect memory of everything that ever happened in math, but do you believe me that you've seen this? Okay, this is standard in pre-calculus or college algebra, whatever you took. It's also standard in intermediate algebra, so it happens a lot. And then also forgetting it happens a lot too. So now you're seeing it again. But now we want to go to really different. What if instead we wanted 1 plus x? Instead of to the 3rd or the 20th, what if we wanted it to the 1.5? Can you FOIL? Will foiling work? Because technically 1 plus x to the 20th, you could FOIL that out over and over and over again. That would be a nightmare. It could happen. You wouldn't want to. But what about 1 plus x to the 1.5? Yeah, foiling does not work on this. Okay, so does that mean you cannot write it as a polynomial like I did above? What do you think? Yeah, the answer is we can write it as long as it's an infinite polynomial, because at x equals 0, so let's do Maclaurin because that's easier. At x equals 0, this is very, very much differentiable. There's no problems with taking derivatives you can use the power rule all you wanted all day long. And as long as x isn't -1, you have no issues. Is that clear? The derivatives are not a problem for this as long as x equals 0. So that means that this does have a Taylor series. So now I'm going to jump to the answer in general. Instead of 1.5, we're going to be looking at any number. Okay. So let me show you the big theorem. And that is for any real number r, 1 plus x to the r power. So in this example, we're looking at 1.5 power is equal to 1 plus rx. And then it's kind of like this binomial that happened. It's going to be r times r minus 1 to the over 2 factorial x squared. So notice when I had a 20 here, it was 20 times 19. Do you see that? Over 2 factorial. So it still works. And the nice thing is what this theorem says is that you can generalize what you do for integers or for whole numbers. And that will work for anything. But for anything, you have to go forever because you never end. If you keep subtracting 1, it never goes away. You'll never get to 0. Whereas if you started at 20, you'll get to 0, but that'll never happen with r being a non-integer, okay, in particular not a natural number. And then you have r times r minus 1 times r minus 2 over 3 factorial. And that's kind of like 20 times 19 times 18 over 3 factorial. Do you see the similarity? Times x cubed. And then plus dot, 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 and actually I need to go plus dot, dot, dot. Okay, and then plus dot, 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 and then it says r times r minus 1 times r minus 2 times dot, dot, dot times r minus n plus 1 over n factorial x to the n, and then plus dot, dot, dot. Any questions on this theorem? Any questions? How do you show this theorem is true? How do you prove this theorem? You use it, you can't prove by example. So using it would be by example. So you can't do that. The hint is think about the quiz you just took, especially question 1. Okay. So I don't hear you, but you just draw a table and you see what the pattern is for the derivatives. Okay. So we're going to expand. We're going to find the Maclaurin series because this is a Maclaurin series. And let's do it. I think it's worth seeing because it doesn't take that long. Is I make a table. We have n. We have Fn. Of x. And we're going to have Fn as 0. If n is 0, then it's just 1 plus x to the r. Let's do it this way though. Okay, and plug in 0, you get 1. So far so good. I got my 1 because that's what the theorem says. Now n is 1. If n is 1, well, it's a very simple derivative. I use the power rule. R times 1 plus x to the r minus 1. Plug in 1, we get r. Any questions so far? Okay, and it's 2. Take another derivative. R is a constant. Constant just stays there. So you just get R times, power rule says multiply by R minus 1 to the R minus 2. Plug in 1. Oh, sorry, it's I forgot the 1 plus X. There we go. Plug in 1, and you get R times R minus 1. You see it working? Okay, and then we can see the pattern and make it happen. The full proof is by induction, but you can kind of see what's going on. Any questions on this? Notice we take a third derivative, the R minus 2 goes over, you get R minus 1, R minus 2. That was the next one, and then you just keep going. So this is just doing it, but it's such an important series that it's one of these theorems and you want to remember it forever because it comes up for some reason all over the place. My last sabbatical I did on looking at applications of mathematics. And for calculus, this was the #1 application I found. Okay, it happened more than any other application. Isn't that kind of weird? And don't ask me why. You know, I'm just a math guy, but for some reason, every field uses it. Any questions on the binomial series? Okay, let's do an example. Once you have the series down, the examples are simple. But I think I'm gonna. And that is, let's see if we can find 1 minus x to the 2/3. So why is this not exactly the binomial series? What's wrong with it? Yeah, it's a 1 minus x instead of a 1 plus x, but that's not a problem. That's the good news, is that you're always allowed to use substitution when you're doing a Taylor series or a path. So everywhere you see an x in the formula, you just put a negative x. That's all you have to do. So I gave this example so you'd remember to do that. We're going to do it again many times. So let's take a look at this. So we can say f of x is equal to, you can have 1, and then plus, what's r in this case? So I'm just looking at the formula here. What's r for us? Yeah, r is 2/3. So it's going to be 2/3 x. And I think, yeah, I probably want to do it with the fraction. So 2/3x. And then plus, and then we have r times r minus 1. Well, r is 2/3. 2/3 minus 1. Oh, yeah, and that's, sorry, that plus is a minus. Because instead of x, we have negative x. Okay, so again, we have 2/3 for the r. R minus 1 will be negative 1/3. So it's 2/3 times negative 1/3. So that's going to be, let's write it out, 2 on the top. And then 3 times 3, because thirds times negative 1/3. Okay, and then over 2 factorial. 2 factorial is just 2 times 2. And then x squared. Negative x quantity squared is the same as x squared. And notice we had a negative sign, so it's a minus. Stop me if you're not following something, because I'm talking it and then writing out the answers. Okay, then we do r times r minus 1 times r minus 2. So Again, that's going to be 2/3 times negative 1/3 times negative 4/3. So that's 2 negatives, right? And then we're going to have an x cubed. That's going to give you one more negative. You have 3 negatives, so it's a minus. Then we're going to have the fraction. And again, we had a 2/3. We had a negative 1/3 and a negative 4/3. So 2 times 4. And that's going to be, I'm going to write 3 cubed times 3 factorial. And that's going to be times x cubed. Any questions on this? Okay, and at this point, I think I'm going to go plus ... Because again, you can see there and see, find a pattern and stuff like that, but I don't want to spend all day long just doing that. Instead, I was able to find the 3rd degree polynomial and note that I could find more if I needed to, as high degree as I want. Okay, or if I were doing it personally, okay, if this were, this were for my work, not teaching work, but let's say I had some other work I had to do. How do you think I would do this? Because it's important for you to have these strategies too. Let's say I wanted to go up to the 100th power to get a really good approximation. Any guess on how I would do it? For those of you who actually want to use math someday, or you need to know how to do this. No, here's what I would do. I would write a computer program code, and I would code up r times r minus 1 using a for loop, have the computer multiply those out, and then another for loop with the plus signs, and then have the computer spit out what the answer is up to 100 power. Okay, that's the real world. And I like to remind you what happens in the real world. Nobody does this by hand. But if you don't understand how these formulas work, and if you don't understand how to program a computer, you're not gonna be able to do it. So let you know that that's kind of the purpose of this, is to understand how these work and eventually get good at coding. Again, I strongly recommend, if you've never taken a computer programming class, nowadays it's just necessary for STEM, for like hard science majors. Okay, it's just something you're going to have to do. So that's how I would do this. I would code this up. It'd probably take me 10 minutes to code this up, but that's because I've been programming all my life. Okay, and then the computer could do whatever it needs to do. So I want to let you know, the real world. Okay, I am not going to have you code anything in this class because I can't assume you know how to program a computer, but I strongly encourage you learning in terms of long-term career stuff. Computers aren't going away, that's for sure. Any questions on this theorem and the using the binomial series? Okay. By the way, just a note, what's the radius of convergence of this series? Yeah, it's 1. And we know that because things go wrong at x equals 1. All of a sudden, you can't take a derivative. And we had a theorem that as long as you can take an unlimited number of derivatives, your radius of convergence is until you get to where you can't. And again, you can't at x equals, when x equals 1 on that one, because then all of a sudden you're going to have a 0 to the negative 1/3 power for the first derivative. So that means the radius of convergence has to be 1. Okay, so the radius of convergence is as far out as you can go so that it is infinitely differentiable. Any questions on this example? So let me know. the radius of convergence for the above is 1, since at 1 or at x equals 0, it is not differentiable. And it is before 0. Okay, and for all is, if x is negative, it's fine too. So you're okay, but you hit 0 and then you're screwed. Any questions on that? Okay. Now I want to do an example. It's actually nothing new on this one, but it's so important it needs to happen. And this is called Euler's formula. I think it's one of the prettiest formulas in the world. Okay. So let's see if we can find and simplify the power series expansion for f of x equals cosine of x plus I sine of x. Do you guys remember what I is? Yeah, it's the square root of -1. And for e to the ix, and we're going to look at those two things and see what happens. Any questions on that? Okay, and they're not hard. We've already actually kind of done these. So do you remember, because I already did this one, cosine of x. Do you remember the series expansion for cosine of x? You remember this happened 2 days ago. I did sine and cosine. Okay. Yeah, so it's -1 to the n over 2n factorial x to the 2n. So I'm going to make it all pretty. -1 to the n over 2n factorial x to the 2n. And how about sine of x? Do you remember the formula for the sine of x? And the hint is the cosine of x is an even function. That's a hint. The sine of x is an odd function. So do you remember? Yeah, it's the same thing. And that's why I'm copying and pasting. Take that cosine, turn it into a sine. And we're going to have, instead of 2n, you're going to have 2n plus 1. Okay, so in particular, now I can look at this. And say that is equal to the sum of the two series. I know it doesn't look great, but it's going to be good. I promise. Any questions on, and I need an I, sorry. So I'm going to throw an I right there. It's I times the sine of x. Any questions on finding the power series or the Maclaurin series for cosine of x plus I sine of x? All right, now we need to find the Maclaurin series for e to the ix. And actually, I think I'm going to do the following. Let's do the table. So we have n, we have fn. Let's see, do I need to do a table? Actually, I don't need to do a table. I think I'm going to not do a table. That's going to take too much time, and we can do it a different way. We can look at e to the ix. And you know the power series for e to the x. What is the power series for e to the x? Yeah, it's x to the n over n factorial. But we're actually looking at e to the ix. And what you're allowed to do is you're allowed to just substitute ix for x. That's how power series works. So I can write ix to the n over n factorial. Any questions on that? All right, now I think it helps to expand it out. I really do. So now, if n is 0, you just get 1. If n is 1, we get ix, period. If n is 2, we get I squared x squared over 2 factorial. What is I squared? Minus 1. So then we get a minus, and then a fraction, and we're going to have x over 2 factorial. Okay, now if n is 3, oh yeah, I'm sorry, not x, but x squared. If n is 3, then what's I cubed? So what is I cubed? How do you simplify I cubed? The idea is, yeah, it's negative I, because I cubed is I squared times I. I squared is negative 1. Negative 1 times I is negative I. Any questions on that? So it's going to be minus I, and then we're going to have x cubed over 3 factorial. What's I to the 4th? That's 1. I don't have to write 1, I'll just write plus. And now we're going to have the fraction, x to the 4th over 4th factorial. Okay. And I think I'm going to do a few more because it's important that we see what's going on. So the next one, if we do I to the 5th, that I to the 5th is I. So you can get plus I. And then x to the 5th over 5 factorial. Etc. So here's the trick. Let's write this as a combination of the real part and the imaginary part. So this is equal to, let's do the real part. That's going to be 1. That's real. Ix is not real, so don't write that in. And then minus x squared over 2 factorial. And then the next one without an I is going to be plus x to the fourth over 4 factorial. And I'm just going to write plus dot dot dot. And then plus, now let's do the imaginary part. We're going to have I times, and the first one will be x. And the next one will be minus x cubed over 3 factorial. And then the next one will be plus x to the 5th over 5 factorial. And then plus dot dot dot. All right, I'm going to put parentheses, even though you don't need to, I'm going to put parentheses around the first piece and the second piece. What is this equal to? And this is a big, big, big theorem. If you look at 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, the next one will be minus x to the 6th over 6 factorial. What's in the parentheses here? Anyone see it? Here's a hint. There's a reason why I asked you to do these two sets, cosine x plus I sine of x and e to the ix. What's in these first parentheses? Okay, they're all even, but they're better than even. Okay, this is an x to the 2n. This is a 2n factorial. It's alternating, so there's a negative 1 to the n. This is cosine x. The first part is the cosine x. That's what that series is when you expand it out. So the amazing thing is we can say this is equal to cosine of x. And similarly, plus, how about this piece? What's this equal to? Yeah, that's a sine of x. So plus I sine of x. So that means e to the ix equals cosine of x plus I sine of x. Any questions on that? Okay, now I don't have time to do this, but also you can reverse this and you can say that the cosine of x is equal to e to the ix plus e to the negative ix all over 2. And similarly, you can say that the sine of x is e to the ix minus e to the I. Oops. E to the negative ix all over 2i. Okay. The proof of this is very simple. you just take cosine squared plus sine squared and you realize you end up with 1. That's all you have to do. So that's basically the proof. What this tells you is that sines and cosines are exponentials. I don't know if you've ever seen that before, but it's a big deal. So as soon as you get into advanced physics, for example, you never even talk about sines and cosines anymore, because then you have to deal with all the trig stuff, and trig is a pain in the you know what. So it's a lot easier to do exponentials. Exponentials have beautiful, nice rules in dealing with it, but you got to live with complex numbers. Okay, and that's the punishment to do this. So you have a choice, trig or I, and most people think I is easier. Okay, so all of the trig identities and stuff, they're so easy to prove using Euler's formula. So I'm not going to go any further than that because I want to do some more stuff. And that is solving a differential equation. So I'm going to do it by example. Once you see an example, you kind of get what's going on. And the example is solve Airy's equation, which is y double prime minus xy is equal to 0 when y of 0 is a and y prime of 0 is b. Okay, and I'm going to let you know there's no nice, easy way of doing this. But what can we use? Here's a hint. What have we been doing the last weeks? In 2 words, what can we use? Yeah, power series. So what we're going to do is when you want to solve a differential equation and you don't have like a nice tricky way of doing it that's easy, you jump to power series. So let's go to power series. So what I'm going to do is I'm going to say y is equal to the summation n equals 0 to infinity of, I don't know what it is, so I'm just going to say it's an x to the n. I can always say that, right? Okay, we're going to assume that it's differentiable so you can do it. Any questions on that? Now from before, we need to find y double prime. Well, what's y prime? You got to find y prime to find y double prime. Y prime is equal to, so hopefully you remember how that formula works. You just take the derivative. But there's one little adjustment. So let me ask you, what's wrong with saying use the power rule -1, and then we're going to have an n here. What's wrong with that? Oops. And there we go. What's wrong with that? There's one little subtle piece that's not right. And I mentioned a couple days ago. Anyone see it? It's very subtle, but it's important. Yeah, you can't start at n equals 0 anymore because x to the n minus 1, all of a sudden you're taking a 1 over x. That's not even differentiable. That's bad. So we start at 1. Now I don't want y prime, I want y double prime. So guess what? I take the derivative of y prime. And that's going to be y double prime. Where am I going to start at now? If I take another derivative. Yeah, now I have to start at 2 because we took another derivative. Every time you take a derivative, you start at the next value of n. So now we're going to have n times n minus 1, just using the power rule again, x to the n minus 2. Any questions on that? Now I just plug in. Okay, but one of the problems is that, you know, I can multiply by x, that's fine. So if I do that, let's plug in, I get y double prime. So there's y double prime. And then minus, and then it's xy. Now, if I multiply this series by x, what changes here? If I multiply by x, what changes? Yeah, it becomes an x to the n plus 1 instead of x to the n. That's the power rule. All right, now here's an issue. And the issue is, I want to combine these two, but I can't combine them because this one starts at 2 and this one starts at 0. How do I change that? I want to do a couple things. Even more importantly, it would be nice if instead of an n minus 2, if this were just an n, or sorry, if this were an n plus 1. And I want to make that an n plus 1 because I want the same power of x's. And the way you make it an n plus 1 is you substitute. So if I let u equal, well, if I let u equal n minus 1, then that would be an n. Okay, so I want it to be an n plus 1, or a u plus 1 if I want. So if I let u equal n minus 2, I would get a u. But if I let u equal, so maybe I'll write it this way. We want n minus 2 to be equal to u plus 1. And that way I'll get the u plus 1 power. Any questions? So if I want that, then u is going to be equal to n minus 3. Any questions on that very basic math, but it's kind of tricky to come up with the idea? All right, so now if u is n minus 3, then I can rewrite this guy. Let's do that. And whenever I see an n, so if u is n minus 3, then n is u plus 3. And in particular, for example, if n is 2, then I'm going to start at negative 1. Any questions on that? Because 2 minus 3 is negative 1. And then n is u plus 3. U plus 3 minus 1 is u plus 2. And then n again is u plus 3. And n minus 2 was u plus 1. Any questions on that substitution? Okay, now more tricks. This kind of tricky math. This is going to be equal to, well, I'm going to just pull out the negative 1 term because I want to start at 0 so I can add these sums up nicely. So if I plug in negative 1, what do I get? Well, let's look at it. Very easy. If u is negative 1, I get 2 times 1, which is just 2. And then I have a sub 2. And then if u is negative 1, I get x to the 0. So it's just a sub 2. It stops there. So 2a sub 2, and then plus, and now I could do the same thing, except now since I pulled out the -1, I now get to start at 0, which is what I want to start at. And now I'm going to play one more trick. And that is the letter U is meaningless. I could use any letter I want and I get the same answer because we're just plugging in these one at a time. So I'm not going to use U anymore. I'm going to use N. I'm going to just change the letter to N, and that way it'll look like what I want it to look like. Now I can put these together because that was the whole point. And what I can get is that y double prime minus xy equals 0 becomes, well, y double prime was this one. Except, oh, I forgot to change the n is -1 to n is, that should be a 0. Like so. All right, and then I'm adding this guy. And the good thing is, since they both have n equals 0 to infinity, I can just add them up like that. Oops. Got to hit paste, copy. Let's try again. It's minus, though, not plus. And then I can factor out the x to the n plus 1. And that's kind of the whole point of all this stuff. So it's equal. And I can factor out the x to the n plus 1. If the computer let me do it. Like so. Anyone lost on what I just did? It's a lot of little algebra steps, but there's a bunch of them. And that equals 0. All right, so then finally I can start realizing that if it equals 0, I can write this out and look to see what happens. And for example, if I work this out, I get 2a sub 2. If n is 0, I get 6a sub 3. And then minus a sub 0. And if n is 0, that's an x. And then plus. Okay, and then if n is 1, then I get 4 times 3 is 12. A sub 4. Minus a sub 1. X squared. All right, now to note, by the way, we know that y of 0 is a. Well, y of 0 is a0. Okay, so that means that a0 is equal to A. Similarly, y prime of 0 is A1. And that tells you A1 equals B. Okay, well then, because if I have a polynomial equals 0, then I know every single coefficient must be 0. So here's a coefficient must be 0. That means A2 is 0. Okay, here, this one must be 0. But A1 is A. So that means that A3 is A over 6. Okay, this guy must be 0. A1 was A1 is B. So that means A4 is B over 12. And I could do this forever. I have dot, 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 but I could keep doing all these. I could even write a recursive formula for this and make it work. And this is the idea of solving differential equations with power series. Any questions on this? All right, the very last thing, has anyone taken stats in this group? We have anyone that took a stats class? Okay, good. A couple of you have taken stats. What's the most important distribution in stats?
Binomial.
No,
Or normal.
normal. Normal is the biggie. Binomial is a nice one, but normal is the most important. There's no question about it. Okay, normal distributions are important. And when you took stats, how did you learn how to find the probabilities with the normal distribution?
Standard deviation.
But how'd you find it? How'd you get your number? For example,
You have
if
data.
you,
You have data.
no, without data, if you want to, if you have a normal distribution, you want to find out the probability that you're, say, between 0 and 1. And let's say it's standard normal.
Or you graph it.
You graphed it, you probably used a calculator, right? You never really learned. You just think you learned, but you really never learned. You learned how to use a calculator. That's all you learned. You learned how to visualize it. And the reason why you didn't learn is you hadn't had this class yet. So I'm going to do this really fast. You only have a few minutes. But the standard normal distribution is defined by 1 over the square root of 2 pi e to the negative x squared over 2. And the probability of a random event being between A and B is defined by the integral from A to B of f of x dx. Okay, you don't get that in elementary stats because it's just too hard. You just graph it and you shade an area under a curve. Yeah, you don't ever talk about integration, but area under curve is integration. All right, so if you want to find the probability that a randomly selected outcome from a normal distribution, okay, a standard normal distribution, is between 0 and 1, well, we need to integrate this function. So let's write it out in the 1 minute I've got left or so. So now we're in between 0 and 1. We're going to integrate from 0 to 1. Our f of x is this 1 over the square root of 2 pi. E to the negative x squared over 2. I'm going to take the 1 over square root of 2 pi. And I'm going to, let's see. Pull it outside the integral. It's just a constant. I can do that. Do you remember how to integrate e to the negative x squared over 2? The answer is you don't remember because you never learned how to do it. Okay, but here's what we can do in 2 words. Any guess? U sub won't work, by the way. You can try all you want. U sub will never work. Yeah, power series. So I can rewrite e to the negative x squared over 2 as a summation n equals 0 to infinity. Remember, e to the x is x factorial over, x to the n over n factorial, but we have e to the negative x squared over 2, so we just kind of adjust, substitute basically. The negative becomes a negative 1 to the n. X squared becomes an x to the 2n. Over 2 becomes an over 2 to the n. And then n factorial. But this is an easy integral. Integrating is really easy with power series. So now let's integrate. And that just says we divide by 2n plus 1. We add 1 to the power. And we're going to go from 0 to 1. See if it lets me do that somehow. No. So I'll do it this way. And then plug in. And when you plug in 0, you get 0. When you plug in 1, the x's all go away. So what we get is the summation. We still get the 1 over 2 pi, root 2 pi. We still have a summation. And then we're going to have a negative 1 to the n. The x to the 2n plus 1 just becomes a 1 when you plug in 1. Over 2 to the n factorial, 2n plus 1. And there is our answer to that probability. That's the exact probability. And if you wanted an approximate probability, notice this 2 to the n factorial, 2n plus 1. If n is even 5, this is huge on the bottom, which means that you don't have to do very many to get a really good estimation. If you do 3, you'll probably have 5 decimals already, maybe 3 decimals. Okay, you don't need a very big n. And that's it. But we're out of time. Sorry, I took a little extra, but happens sometimes. So I'm going to stop. And I'm going to stop the recording.